right. Well, next up, I'd like to welcome to the stage Margaret Caserga, who will be discussing, instead of harvesting light, we're going to talk about making light, like LED.
Thank you very much. Hello, my name is Margaret, and I'm a founder and a CEO of Lighting Charge Solutions. And today I would like to talk about materials, so let's take it to the chemistry level, supply chain, for electronic devices. And in particular today, I'll be talking about organic lighting media diodes and their application in lighting as well as displays for your smart watches, cell phones, TVs, and so forth. Now, let's talk about what are the current problems in the industry. After having a large different variety of customer types and talking to them, what we found out was the fact that there is a lack of appropriate materials that are essential for the light emission actually in the OLED devices. And the mismatch in electron hole transport materials results in the very complex manufacturing steps to make the emitting layers function properly. So the problem, we don't have the right materials, which results in a very costly, hard manufacturing for large-scale printable applications. What is our solution would be to make materials that can be colored to a particular customer need. They'll be architecturally adaptable to the different device designs. They'll be made of earth-abundant materials so we can decrease the cost, and they could be made on a large scale while being all appropriate for the current manufacturing capabilities. So our value proposition would be to enable those companies access new revenue streams by allowing them to produce those alternative products that they're trying to make. Now, I'm skipping slides here. So what is our technology? So our technology is a platform of these materials. Let's go behind me. Of these hexacoordinate silicon compounds. And what is this technology based on? It is all earth-abundant metal based instead of having the rare earth metals that you commonly see in the industry nowadays. But they're also very simply and rationally tunable to different applications. So here we see a demonstration of blue, yellow, and red, which are very common in the industry, as well as some greens. And we have demonstrated that we can tune it specifically to the need. What is also a great thing about these materials is the fact that we can manufacture very high quality smooth films. And why is that important? Because any roughness in the materials makes shorting sites in the devices, so our devices burn faster and the manufacturers are not happy with that. But another very interesting thing that we found out about materials that is very exciting and makes us think that we are capable of doing this is the fact that these materials can very efficiently at the same rate transport both electrons and holes, so that way they can meet at the interface and emit light. This is very important. This is how we're going to be able to decrease the amount of layers that are needed, because we won't need to use separate materials for that. As far as the prototypes, we have been able to demonstrate successfully organic photovoltaic devices and using the electron transport materials, field effect transistors, and OLEDs. What I want to point out about our organic light emitting diode prototype here to your right is the fact that the picture you're seeing here is actually that single layer emitting device. So we only have a cathode and anode and one layer of organic material. Why is this important? This proves the concept that we have very successful prototypes and we could move on further with this. Now, our game-changer technology would be not just only moving to that single layer because that exists, but really understanding why are we failing to scale up and do this at a large scale in the industry, while in the laboratory people are very successful at this. So the idea behind is to decrease the amount of layers, so we would simplify the manufacturing, because once you move to printable roll-to-roll or inkjet printing, the more layers you have, you start to dissolve the underneath layers. So you're killing your efficiency as far as production manufacturing, as well as the more amount of layers you have, the more energy they would require to actually emit. So you're putting a lot more stress on the grid, so there are multiple assets to that. Now, if we're going to start approaching this single layer as close as possible with that single material or maybe even dual material, but you can just print it all in one go. That would help the manufacturers to make those large panels for lighting purposes as well as your large screen TVs without having to deal with all sorts of manufacturing issues of multi-layer stacks. And another important thing to do here would be to make sure that we can work with the current manufacturing capabilities of the industry. So this would be very important to us as well in our scale-up process. Now, what is our opportunity? It's a very saturated space right now in the OLED market, and there are some big players that are international, like Samsung, LG, and BOE. And to make our way to that big company like that, we have to focus first on the local market and the manufacturing companies that are here in the United States and maybe internationally as well, but that we can quickly communicate what are their needs and accommodate them quickly to build up our prototypes and build up a product line securely. So after our customer discovery, we've already secured one of the customers with Synovia Technologies. They are doing a roll-to-roll printing, and they came to us with a very specific problem. They cannot make the panels that they've been ordered to produce and sell because their materials are not matching what's currently used for the emitter. So they're not able to even produce the panels they've been requested, so they're not even able to access their revenue. And having the materials that would allow them to do that would access their revenue line. This is a great news for us because this is what we're approaching. We're approaching that printable display technology, and we're providing materials that would make that happen. So when we're looking at our target market, $10 million a year would be for that single layer product for the local market to enter in the first 5 years to secure a space in the industry and then move on and scale up to the larger type of manufacturers. Okay, and our go-to-market strategy would be in the first year to start sell our first generation and second generation of printable and solid state evaporation materials to the first customers to receive that valuable feedback that we need about what are the failure modes, what else do they need to do with these materials, and then we could accommodate them efficiently. So with the help of CRI and Argon, I'm hoping to access that 2022 deadline with the third generation materials that would ideally be that single layer emitter layer that could be roll-to-roll printed into a display panel. And then within 5-year mark would have solid customer set for the small manufacturers to medium manufacturers in the local and maybe even international market. And then our 10-year goal would be that scalable large company supply chain. Now, how do I want to do this with help of Argon and CRI? This would be an incredible opportunity for a company to achieve these timelines in the time fashion that we need to be achieving. So after speaking with Yana Roshkova, she was able to direct me to Yupen Zhang as well as Jay Shu. She's in the audience. Thank you so much for being here today. We were able to discuss with Jay Shu specifically that we would have to start with our current prototypes because I have not been able to test them, and printing technologies would have to start there. There are instrumentation here available, there's manufacturing here, and people know how to do it here. Would start there, access the failure modes, see what our compatibility issues are, and then have the iterations for a third generation printable materials, and so we can target the particular functionalities, very particular adaptability for the printable applications. And then by the 8-month mark would be testing these third generation materials in printing of devices. And by 12-month mark would be actually giving those materials to the customers to receive their feedback, so that by 18-month mark here would have another chance of addressing those issues and reiterating on them for the sale by the 24-month, and hopefully earlier. I'm trying to access the sale by the 18-month mark for these types of materials. Now, who are the Lighting Charge Solutions? So I'm the founder and CEO, and I have a co-founder, Tom Schmedicke. He's also my current technical mentor on these materials. I'm working with Kristen Dillinger, who is my industry mentor, helping me to bring my laboratory scale idea to the market because she's a professional in that area. I have entrepreneurial lead Damian Bisog that is helping me to conduct customer interviews because we have to talk to a lot of people to understand what the issues in the industry are so we can accommodate them. I have two device mentors, molecular device mentor Michael Walter and Yang Zhang for electrical computing engineering on the ideas on how to make these ideas possible at the scale that is needed for manufacturers of display and devices. And I'm also receiving help from my marketing interns for business and marketing for local US market as well as international. Since I'm a scientist, I try to seek help from the other resources to access that market quickly because there are very specific deadlines and things we have to do. And with that, I would like to conclude and give a few reminders that what is a problem? Lack of appropriate materials that make large-scale printing of OLEDs accessible and efficient. What is a solution? Making these materials that would be color tunable and architecturally adaptable to the manufacturers that would be using these materials. Our market would be OLED displays as well as OLED lighting panels, and specifically manufacturers and the engineers of that industry. And a 5-year projection would be a very minimal revenue of 4.5 million a year, but I'm currently revising that number as we are getting better understanding of what is the scale like out in the industry right now with our customer discovery. And with that, to get your questions. Thank you.
Thank you, Margaret. I would like to open it up to the panel. Who would like to start us off with questions? Jason.
Can you explain how your material works?
As of in the device?
Yeah, I mean, I'm not that good at this stuff, so
Okay.
how does it work?
Yeah.
You kind of gave like what it does, but how does it work?
So fundamentally, to make any OLED panel to work, you have to have electron what's negatively charged and a hole that's positively charged from cathode and anode to meet together and recombine radiatively and emit light. That's the fundamental goal. That's all we need to do: transfer electron, transfer a hole, emit the light. So what I'm capable of doing with one layer is the fact that the electrons and holes transfer at the same time within my material because they travel at the same rate. And then currently they're self-emitting fluorescent, which are not very efficient, and our goal here would be to move them to that triplet full efficiency emission. But yes, so we're just fundamentally with single material traveling the electron and hole together, driving them together, emitting light.
Yeah, and the other folks need a bunch of layers to do that. So what are you doing that you don't need the bunch of layers?
Yes, so the fundamental problem of why you actually need so many layers right now is the fact that you have materials that are very good emitters. Then you have materials that are very good at electron transport. But then you have materials that are very good at hole transport, but not one thing. But then you have to have material that would be hole blocker or electron blocker because you start to get leakage because of the mismatch on the transfer rates of electron and hole. If electron gets there faster and the hole gets there slower, you lose your efficiency. So right now, all of these jobs ended up being separate jobs for separate layers. So what we're trying to do, having that same rate and making sure that we keep that same rate as we alter our materials, we can accommodate the fact that we won't have to have the 20 layers to do so, and one layer would be able to do that.
Okay, and sorry to keep asking questions, but what's the magic thing that you're doing that you don't need 20, you turn 20 into one?
Molecular design. It's really how these materials designed rationally to stack in a particular way that would secure that type of transfer and that kind of emission. Yes, so just molecular engineering pretty much.
Yeah, I guess I was good. Very impressive. I'm going to ask related to like how many degrees of freedom do you have with this hexavalent silicon compound to be able to get the type of performance? So like where do you need to go in performance? Maybe it's a specific colors or brilliance, or you mentioned some triplet state. Like, and since you have one essentially compound that you can put decorations on to affect this, like, do you have enough room in your chemistry to be able to do all the things that you need to do from a performance standpoint?
Okay. There is definitely room, and our patent is securing every possible variation of the hexacoordinate silicon compound, and there's a lot of ligands currently known to be done with that. So particular alterations impact either different homolumo, which would be accommodating to a particular color requested from a customer that we would be having, as well as depending on what kind of decorations we put would be altering how they pack and would alter the rate of transport for electron and hole as well. So yes, there are very much a lot of room for that. The only kind of thing that I don't have an answer to right now is efficiency factor, which I would need to be in a place like Oregon where there is equipment and knowledge on how to measure external quantum efficiency, because that would be something we have to accommodate in order to be competitive. We want to be better than what's currently existing, right? Otherwise, there's not really a point. So we know that we are at least comparative to what's currently in the market, and oftentimes even better because of the properties that have been improved. We're way more stable with respect to moisture. There's no moisture issues with my materials, unlike the current competitive materials, as well as they're a lot more photostable, they're a lot more thermally stable. So this is what we do know, and that's what gives us that sort of thinking that we can succeed with this.
Eric.
Yeah, you sort of answered most of my question at the end there. Bleaching was obviously a big problem with OLEDs for a long time. Some of these things look like they might be reactive with oxygen. Have you spent time looking at that?
So we did briefly enough to where we monitor material over a long period of time with respect to moisture and air. Photo bleaching studies in comparison to some of the current competitive materials, we have seen tripling of stability in presence of oxygen. So this gives us hope that this would be successful if we can at least triple right now, and then in the future ambitiously would hopefully eliminate the encapsulation altogether. That's a long-term goal.
Bill.
I'm not sure this is the right question about efficiency, but are we talking lumens per watt? What is the efficiency? Okay, it is lumens per watt. Okay.
So yes, and then that would be something we'd need to do, because right now it is possible to achieve 100% internal quantum efficiency of everything emitting correctly within the material, but then there's problems of extraction of external efficiency due to waveguiding and other reasons. So yes, that's what we'll be looking at, is lumens per watt efficiency.
SJ.
If you don't get into CRI, what's your plan?
So right now I have some amount of seed funding currently that I could use, as well as I would be applying for the user facilities here, which was great news for me today, and in the talks that I've been kind of talking to people, and especially Dr. Shu, she said that we can still work together and find a way to get those important efficiency information that we have to, in order to be able to speak in the language of the engineers, manufacturers. So it would be great. It would be a much better safety cushion if I got in. But I'm also thinking that regardless, I would like to continue with the connections that I've already made here, and then people have been very welcoming and addressed those issues regardless. Yes.
Yeah, I was wondering specifically what resources you'd be using at Argonne.
Yes, so in Dr. Shu's lab, she has a different type of printing technologies for solution printing. And then after speaking with people from Murph as well, they're receiving new inkjet printers as well as roll-to-roll printers that will be up and running by about April, May. So I'm really looking forward to access those as well to see the actual manufacturing capabilities. This is my step one. But there's also lots of great optical technologies in the Center of Nanomaterials here to actually study the efficiency, study what are my failure modes, and be able to successfully address them.
Dr. Carlyle.
Margaret, I think you've answered this question, but I can't resist. So if I put a gun to your head and said you had to roll out square yards of this stuff, indium tin oxide roll to roll, and you apply a voltage, am I going to see a big honking uniform nice green color? Or what's the gotchas? What keeps you up at night? I mean, what's just sort of preventing you from from making something that nobody can come close to making with the simplicity and the cost structure that is implied by your presentation?
Yeah, the main problem right now is seeing the compatibility with the printing technology, because I haven't been able to access that right now at the moment. But what we have seen from a customer discovery is that this type of materials have not been on the market. Unsure of the reasons why there are no ambipolar hosts available of electron hole transport at the same time. It could be synthetic procedures, because I've talked to people that make them. It's like 20 steps down the road. But yes, my main problem right now is the fact that I have to address the printability question. How would they print? Because my current access is evaporation only.
Any other questions from our panel? Okay, any questions from the audience?
If you were just looking at this as an opportunity to provide new materials for the emissive layer in the traditional manufacturing of OLEDs, would you have any advantages there in terms of, I know there's trouble producing like in the blue efficiently? That was my question. I'm done.
Yes, so this is actually our strategy to the market currently. How about we use the current best emissive layers that the companies have already found out works for them, but make them efficient to where they can actually produce the panels and make them efficient and long-lasting with their emitters that they want, especially like you mentioned, the blues and the greens. There are still a lot of issues with those. So my first market strategy would be to replace what's currently on the market and then just use the emitters already available, while I'm trying to figure out my way of how can I embed it all into a single layer with the 100% internal quantum efficiency. Did that address your question?
You, in your single layer, you're doing the emission there.
Right.
I guess I'm curious how much, going back to the degrees of freedom question with your complex, how much control you have over color quality, color temperature, things like that.
Synthetically, I would have control over the color tuning because I have some access to the computational modeling correlated to my current prototypes. I have a line of about 10 compounds right now ready. So we have a model strategy how we get from deep blue to deep reds. So I already have an understanding how to get there right now at the moment. But as far as a particular functionality for printability, that would be something we have hypothesis, but we have yet to test it. How well would that work?
Well, with that, I think we are out of time for this presentation. Thank you, Margaret.
Thank
We
you.
appreciate it.